Yes.
Thank you. Can you hear me well in the back? Can you hear me? Perfect. So it's a great pleasure to be in Taipei. It's my first time in Taiwan. Thank you, Daniel, and all the organizers. I'm having the time of my life. I was going to talk about amplitudes and QCD, but Daniel told me maybe that's not a good idea. I'll just talk a little bit about black hole physics. All right. So my plan for today is to give you a very informal overview of what we learned in the last 3 to 4 years about what I'm going to call black hole spectroscopy. And I think we've been hearing during the last few days about gravity and how to compute things in gravity. And there's very strong reasons why we care about that. I think the first of all that we should always keep in mind is we do not have a good description of matter in the universe. We know the standard model of particle physics cannot be the final word. We have plenty of robust evidence that things are not working the way we would like them to. But the theory, the description itself of gravity can also not be the final word. And I think perhaps the best evidence for that is the singularity results by Roger Penrose that tell us that whenever you have something forming a trap surface, then something goes wrong, either in the way that matter behaves or in the way that space-time itself behaves. Maybe even the notion of space-time loses all meaning whenever we have trap surface formation. And so this also indicates that maybe a good place to start looking for the final answer or the final description of the gravitational interaction lies close to black holes. This is where gravity is at its strongest. It's also where the most violent, highly dynamical processes occur. And I'll have a few more words to say about it. Now, the problem with these two puzzles, if you wish, is that I don't think we have any idea of where to start looking. Meaning the space of solutions is really just too vast. And if you ask anyone doing, extensions of general relativity, they will tell you, we do a handful of theories because that's the thing we know how to do. We know the equations of motion. We know roughly their second order. We can evolve this stuff, and that's it. I'm not going to go into any of that. I'll just take the easy way. And the easy way is actually located within general relativity. Black holes, I don't think I will tire ever of saying this, are the simplest macroscopic objects that we know of. Any asymptotically flat vacuum spacetime is described by two parameters alone. And those are the black hole mass and the black hole spin. It's truly amazing, and I think you should always, when you're in a room like this, you should always think about what it takes to describe an audience like the one we have here. Okay? And so it's a gift because, well, it should be simple to look for deviations from this prediction. It should be simple to look out there and see or come up with strategies to see if, first of all, if black holes exist, and second, if they do they actually belong to this curve family of solutions? So it's kind of funny that back in '86 or so, in a lecture in Germany, Chandrasekhar was saying, well, the following, that a confirmation of the metric of the curved spacetime or some aspect of it cannot even be contemplated in the foreseeable future. This was 1986, and so we're roughly 40 years, 4 decades after that. And I hope to convince you, well, there's many ways to actually contemplate testing the curve metric, and we certainly have some of them under control. I'll tell you a bit about one of them. The question of the quest of understanding whether black holes exist and whether they belong to the curve family might look at first sight like the task of looking at this guy over here and coming up with an answer concerning which planet are we looking at, okay? And some of you probably know what planet it is, but even if you don't, it's clearly some planet, and there's some eddy currents in there, so there's an atmosphere. You can even, if you stare long enough, you will see what type of atmosphere it's made of. And whether it's Jupiter or not, at some point it's almost irrelevant. Whether it contains the same type of mountains or the same type of atmosphere, it's almost irrelevant. But I would like to make the point, and I'll close this introduction, that doing the same for black holes is not really relevant. Black holes are defined by a very, very special surface, the horizon, and I think we should use all the tools available to actually convince ourselves that they exist out there. Okay, so traditionally, the answer to whether we're looking at a black hole, it's just here. If it's dark and very massive, we know nothing else in the universe that produces these guys, that form, that are stable, so they could exist out there. Okay? And this has traditionally been enough. I am going to actually question this and try to think here whether we really are looking at black holes and how can we quantify the statement that we're looking at the curved black hole. It's very similar. So I'm only going to use, I'm very primitive, I'm only going to use a certain tool that I'll call black hole spectroscopy, and that's really the analog of trying to infer the properties of a resonance system by understanding the spectrum. So something like this. There you go. You have some bell ringing, and the idea is to understand what it is. Okay? This is it. These were a couple of students of mine in Kyoto last year. Now you see the bell. You can understand. There's some simple things. The first is that the dominant mode of the frequency should scale like the inverse size of your bell. Exactly the same thing is going to happen to black holes, but we need something else. All right? So the approach is very simple. I think some of you already mentioned this here. The idea is to look for any dynamics happening with black holes. So you take a black hole merger, for example. Okay, you let it coalesce into some final state, and if you believe the stationary uniqueness results of GR, then the final state should be described by a curved geometry. So the idea now is to look backwards in time, right? You look backwards in time, and what you should be seeing is some space-time that deviates slightly from the only vacuum solution asymptotically flat stationary solution of field equations. So you do to the space-time what you do to sound waves when you want to tell your students what a sound wave is. You linearize against the background solution. And when you linearize the metric fluctuations around Kerr, you find something that looks like this. It's a second order linear partial differential equation with some source term. The source term tells you what exactly is causing the black hole to be disturbed. And this master function psi encapsulates all the metric fluctuations. There are several ways of dealing with this. Since I'm going to think about spectroscopy, the idea is to just go into Fourier space, do a Fourier decomposition, and look at the resolvent of this. Look at the Green's function for this problem. Okay? The poles of the Green's function, we call them the quasi-normal modes. It's exactly the same thing you do when you want to look at the normal modes of a guitar string or something, except that these guys lie on the complex plane. Okay? And when you do the inverse Fourier transform, then you close your contour, and you're going to see that the poles contribute with residues. And therefore, if you look at just the contribution from the poles, it's going to look something like this. Your signal, your waveform H, it's going to be a superposition with some unknown amplitudes of e to the minus t over tau sine of some frequency times t. Okay? Tau is the time scale of your mode. I told you the poles line the complex plane. So this is the complex part of your frequency, and F is the real part of your frequency. And so black hole spectroscopy looks really simple. We just need to get a signal H. We're given a time domain signal H, and we basically try to fit it with some set of exponentially damped sinusoids. Actually, black hole spectroscopy is not too dissimilar from heliosysmology or astroseismology. You just take some star, and all of them are actually vibrating in a lot of their normals. For instance, for the sun, it's a 5-minute exercise to calculate these modes, or at least to estimate the modes. And you will find that the sun has roughly 1 million modes with time scales between 4 and 6 minutes. That's the thing we see when we look out there. The quality factor of our sun, meaning the number of cycles that a mode of the sun does before decaying away, is of order 10 to the 6, 10 to the 9. They're huge. The sun is a very, very good resonator. And this is important. And the modes are, of course, driven by, well, turbulence, which in turn is fed by nuclear reactions. Okay? It's just exciting the system. And you can do exactly the same in black holes. You could just take a black hole, place something around it, an accretion disk, it's turbulent, it's going to stochastically excite the modes, and in fact, if you look at the gravitational wave response of a black hole that's surrounded by this turbulent matter, you see something like this. There's turbulence here, but if you zoom in, some of these signals are actually exponentially damped sinusoids that match really, really well these quasi-normal frequencies of black holes. Okay? Unfortunately, this is just weak. The amplitudes of these modes are so weak that we don't have detectors good enough for them. So for the rest of my talk, I'll be focusing on something that refers to very, very powerful events like black hole mergers. The structure of the poles in the complex domain is here. So again, I'm listing the imaginary part of these modes versus the real part. Remember, they lie in the complex plane. And of course, if you think about the time dependence, the tau is 1 over this omega I. So the thing that you care the most is about what I'm going to call the fundamental or dominant mode, the one with the largest lifetime. Okay? The business in the last couple of years has been trying to see whether we can see more of these modes. Okay? But as a rule, the dominant mode always dominates the signal. And for each angular dependence of your waveform, there's an infinite number. The asymptote to a constant value logarithm of 3 over the black hole temperature. I don't know if this is going to play any role in the future. It's just for now. And if you look at the dominant mode, it looks like this. It has a frequency of 1 kilohertz for a 10 solar mass black hole and a lifetime of 0.5 milliseconds, again for a 10 solar mass black hole. So a city the size of Taipei would live, if it were a black hole, would live for around 0.5 milliseconds, okay? Just because these modes travel at the speed of light. And if you calculate the quality factor, and again, I wish that there's one thing that comes out of here, and that's the quality factors of black holes. It's of order 3 or 5, and this means that black holes are lousy, okay? They are lousy resonators. They don't ring, they thud. That's it. This is a black hole. And this is also why doing black hole spectroscopy, it's so complicated. They don't give us time to. Okay. Now, I was looking at the linear description close to the poles, but of course, you should also ask yourself, well, is this a good description? And if you look at the actual response that's contained in the Green's function of that linearized fluctuation, you will realize that there's several contributions to what the detector finds. Okay? The first is, well, the flat space analog, so something like a prompt response. This would come from the way you close the contour when you do the Fourier inverse. then some signals actually scatter very close to the black hole. They orbit, actually, in this high frequency picture, they orbit a number of times around the black hole before hitting the detector. This is what I'm calling black hole ring down. And some of them, if you look at the Green's function, there's a branch cut at zero frequency. They should contribute some very, very late time tail that looks like some power law of time. Okay? If you wait long enough, ring down, it's going to fade away. You should just see a T2 some power. I think in space, you could think of this as waves, gravitational waves being backscattered by the space-time curvature at very large distances. Actually, this is the state of the art in numerical relativity when it concerns these three stages. These are two papers that came out yesterday, one of them by my student, Dina. And you see the three stages really well. This is the prompt response, the initial stage, something that propagates directly from source to detector. You see the ring down here? Those are really the waves that we're saying they are hanging, they're trapped close to the black hole and leaking out very slowly. And then at very late times, you see this power law tail. There's no ringing, just a slow relaxation to nothing, to the Kerr spacetime. Good? By the way, if you have questions, just... So let's do then black hole spectroscopy, or try to start the game. And as I said, the idea would be to find the black hole relaxing, this part over here, fit it with a set of exponentially damped sinusoids, and get on with it. Okay? Of course, you need data to fit, so you need to start the fit somewhere, and the results do depend on when you start the fit. If you start very late, you should be within the linearized description. The problem is that the power in the signal there is very small, so you want to catch as much power as possible, so you want to go as close as possible, but then you're entering possibly nonlinearities or the regime of tails or initial data dependency. So this is what LIGO did. I think this is a beautiful result. The black solid line, it relates, by the way, to the first event, GW 150914. The black solid line uses the entire signal, predicts the final black hole mass and spin, and from there, the set of frequencies. We know these frequencies to 20 decimal places, okay? So it's here. This is the time scale of the mode versus the frequency. When you start fitting, if you start fitting very early, for example, the green line over here starts 1 millisecond after the peak. The peak is this thing over here, roughly, okay? Then it's close enough, but it's not even within the 90% posterior. But as you go later, 3 milliseconds, 5 milliseconds, and so on, then yes. So I think you can look at this as the first spectroscopy test of black holes ever. It's a beautiful plot. It doesn't look like it just because the error bars are so large. But I think this is really history in the making. And I think you also need to think about where we're going. This was done with a signal to noise ratio of roughly 7, so marginally thin. But in the future, we're going to be seeing these guys with signal to noise ratios of, say, 40 in the near future. And when you try to So if you try to repeat the game for just a louder signal, then the event I was discussing is here, very, very tiny errors, and you can even start probing higher modes. Space-based detectors will be seeing events with signal-to-noise ratios of 1,000, not 40, not 7. So I can't even show you the error here. So that's where we're going in the future. Now, the challenges that we're currently facing or trying to understand, well, there are too many to enumerate, but let me just quickly go through some of them. The first is the strength of the poles. We know how to calculate the pole itself very easily. The residue has been well, we don't understand exactly the entire structure of the residue and how exactly it's contributing to the response. Ideally, we would have initial data, and from that initial data, we would immediately calculate the amplitudes of each of these modes. We would like to be able to reconstruct the waveform with just a set of quasi-normal modes. The problem is these are not a complete set. So understanding how to do the reconstruction is not an entirely trivial thing. In fact, it's a known problem in condensed matter and optical cavity for many decades. One thing, I think a breakthrough in the last 5 years or so was the study of the resolvent, not at the poles, but the entire complex plane. We call this the pseudospectrum. In fact, let me tell you the story about pseudospectrum. This was first studied in fluid dynamics decades ago, right? The idea is to look at this operator over here. We know it diverges at the pole, at what I'm calling the quasi-normal mode. How does it behave close to the pole? And if you do this game in fluid dynamics, it was seen a long time ago that there was some sort of spectral instability in some modes that were reproducing laboratory turbulence much, much better than just a full linear prediction. This is, I think, a famous work by Trefton and collaborators back in 93. If you do the same thing in general relativity, if you look at this norm of the resolvent in the entire complex plane, for extremal black holes, you find something similar. It's the figure is here. Again, these are contours of the norm of that resolvent along the complex plane. You find some similar structure, and it seems to be telling you there's some sort of instability for extremal geometries. Good. So this is all linear, but it's useful to remind ourselves that GR is a nonlinear theory. And this, just having fun again, this is one table where I show you the maximum luminosity in processes we know of. Okay? The most powerful laser is of order 10 to the minus 38 Planck luminosity, where the Planck luminosity is 10 to the 52 watt. Black hole collisions reach something of the order of 10 to the minus 2. In fact, the only process we know of that could reach the maximum limit is black hole evaporation. But this seems to indicate that the merger between two black holes is or should be a very nonlinear process. So how entitled are we to just look at the linearized set of equations? So let's take this to the next order. In fact, we know how to do this to arbitrary orders in gravitational wave amplitude h. Okay? If you expand the field equations to second order, well, it's not a big surprise. You're going to get exactly the same structure for the second order operators, psi2, but now they're sourced by the first order guys, which I call psi1. Okay? As I told you, psi1 has some poles, the linear quasi-normal modes, so they should be sourcing the nonlinear guys, the quadratic modes. Okay? This means that if you're in the ring down stage of black holes, well, then second order quantities, meaning the full nonlinear problem, should contain an exponentially damped sinusoid that will go roughly like twice the linear prediction. Of course, you have a large number of combinations, but the dominant guy should be twice the linear guy. So a few years ago, we tried to actually find a process where we could control the nonlinearities. And the idea is to go again to head-on mergers. You take two black holes, they are equal mass, and you start colliding them with a varying center of mass. So you start at 10% the speed of light, something over here, and you go up to 90% the speed of light. Extremely violent processes. You should be, actually this center of mass energy should be a knob to the nonlinearity. So what you're seeing here, what you're seeing here, well, okay. Well, you're seeing here, huh? What you're seeing here is the amplitude of this quadratic mode, meaning the mode which has twice the frequency of the linear mode, as a function of the amplitude of the linear mode. There should be a way to, I guess. As a function of the amplitude of the linear mode. And it's a beautiful quadratic dependence. And this tells you that the amplitude of this nonlinear mode you're looking for does scale with the square of the linear mode. There is something nonlinear when you evolve a field. This was for head-ons. You can try to repeat, of course, the same exercise for mergers that are quasi-circular, something that's perhaps more relevant to gravitational detectors. And if you define the ratio of amplitudes R as this guy over here, for quasi-circular mergers of equal mass non-spinning binaries, you find a ratio of 0.16. It's small, but it's not hopelessly small. We will be able to see this eventually. Okay? And this is basically probing black hole relaxation down into the nonlinear regime. Next order in wave amplitude h. That result was for non-spinning black holes. We even know how things behave as you vary black hole spin just by looking at the quadratic equation. There's a mild dependence, but it's non-trivial. Okay, so the nonlinear ratio seems to decrease as spin increases. Good. Okay, I think I still have 10 minutes. I would like to tell you about spectral stability and environments. Half of this game we do not understand. I told you that the final stage of black hole relaxation are tails. There's going to be some memory out there as well. These are very low frequency components. And this means that tails should be probing actually a large scale around the black hole. And if you place the black hole in the galaxy, well, tails and memory, for sure, they're going to be sensitive to whatever you place around the black hole. So I think it's a fascinating thing. We know nothing about it. What we do know about is the spectral stability of the black hole spectrum. Let me explain what I mean by that. Okay? So I'm going to slightly change the problem I was given, which was, if you remember, a linear second-order PDE with some effective potential. The effective potential looks like this. It has some structure close to the black hole light ring. Okay. And the thing I'm going to do, because I don't know well how to place a black hole in a galaxy or in some environment, I'm going to model matter by some small thing, some small bump far away from the black hole, okay? And then I'm going to recompute the quasi-normal modes of this effective potential. It's just me being lazy. I do have something more to say about it, okay? So my bump has some height epsilon. It's supposed to be very small. It's mimicking a star or an accretion disk or something. And it's placed at a distance a from the black. If this is unclear, just shout. Okay? So this is the spectrum of that problem. When you vary the distance a from very close to the black hole, or 0, and you start placing the bump farther and farther. Okay? This is the fundamental mode of the black hole. Again, omega I versus omega r, for a bump which is 1,000,000 times smaller than the relevant potential. I don't know if it's clear to all that this means problems. Okay? This means serious problems for whoever is trying to do black hole spectroscopy based on the vacuum predictions of general relativity. If we believe that a matter that's, we call it a flea that's, 100 Schwarzschild radius away from the black hole, and it's 1,000,000 times lighter than the black hole, can cause an elephant to scratch this much, then how can we trust whatever LIGO is giving us? Okay? This problem is known in quantum mechanics. It's actually called the elephant and the flea problem, many decades. And I would like to tell you one solution or a fraction of the solution that we know of, and if I have 1 minute, the other fraction that we don't know of. Now, we measure time domain signals, so we want to understand what it means. What does it mean to have a spectrum like this when we look at the time dependence? I'm going to place some bump, a distance of 30 Schwarzschild radius away from the black hole, okay, with some amplitude. It's not really relevant. You're going to understand what's happening. I'm going to throw a star at my black hole, and the black line is the gravitational wave response in vacuum. Okay? And you see here, there's a beautiful ring down and the power law tail relaxing. The blue line tells you the response when you have this bump. And you see that the initial stage, the ring down stage, the prompt ring down stage, the thing that LIGO cares about is exactly the same. To numerical precision, we can't really tell one from the other. Prompt ring down is located close to the light ring of black holes. It's oblivious to this bump. But if you wait long enough, if you have a good detector, well, what's happening here? You have a bump. This bump actually produces a cavity in your spacetime. Much like me speaking in this room, I have some characteristic frequencies. The room has some characteristic frequencies. I win on small time scales. The room wins on large time scales. It's exactly the same. Small time scales, black hole is winning, black hole ring down. On large time scales, the cavity lets go the high frequency components and keeps the low frequency ones. So at late times, what you see is the new spectrum. You see, the destabilized spectrum, that's this guy over here. It's a very small gravitational wave amplitude, but it's there. So it's clearly destabilized the spectrum. But we should know that it doesn't play a fundamental role in observations. In fact, we can repeat this for a more realistic geometry. I'm not going to bother you with the details, but if you try to do this in real astrophysics or something that looks like real astrophysics, you can't just place a bump in the effective potential. Gravitational wave fluctuations couple to the galaxy, they couple to the stars, to the matter, and destabilization is there, but in a slightly different way. So when you do exactly the same process and you throw a star that lives inside the galaxy, what you're finding is, so this line over here is the gravitational wave response. The bottom line is the fluid response, the star's response. And you see that you find, again, a prompt ring down, the black hole responding, but gravitational waves couple to the galaxy. So at late stages, what you see is actually the modes of the entire galaxy. It's the fluid modes that are coupled to gravitational waves. So I still have 5 minutes. Perfect. Jump this. Now, I'm going to end with with the promise that I gave about testing the black hole nature. You can invert the question, and instead of placing matter or the bump far away from the black hole, there's plenty of room at the horizon. So we can actually also pack something in the near horizon region. Okay? And the idea is the same. In vacuum, black hole ring down only relates to light ring excitation, this guy over here, for example. Okay? Black hole ring down has nothing to do with horizons. So you could think that if you actually place some structure close to the horizon, the prompt response is going to be identical. Again, it's really like having a black hole living in the galaxy, but now the galaxy is close to the horizon. Here's what you find when you start adding structure to the near horizon region. Okay? Again, just some artificial construct. I'm actually doing some type of wormhole spacetime. It's irrelevant what it is. You'll understand the details. I scatter a wave, a star, to pass very close to a black hole. I excite ring down waves. Again, black line is vacuum, pure black hole spacetime. Red line is my wormhole or whatever preference you have for something that does not have an horizon. The initial response is the same. It's the light ring in the space-time. At late times, you find, again, the spectral destabilization. So, let me finish here by saying the following. Black hole spectroscopy has begun. I think it's a beautiful thing. Errors are still rather large, but the relaxation stage does inform us on the final state conjecture that whenever we have black holes interacting, they're going to produce a curved spacetime. They also inform us on the near horizon physics and environments, and also nonlinear effects. There's a huge activity going on in the last 2 years. Of course, you might argue that, if I do a nonlinear numerical simulation, these are all there by construction, of course, right? So what we're doing actually is dissecting each part of the signal until we understand that every single prediction from GR is there and we can actually test it. The environments, I tried to convince you that they will always destabilize the black hole spectrum, but honestly, it's the one item that I think we need to put some serious effort. I can't believe that we're going to even discuss seeing memory effects or tails without giving a thought to real astrophysics. Large scales will play a role at lower frequencies. Echoes are a very general feature whenever you try to add some structure to the near horizon. There's no fine-tuning here. You always get this. And of course, I didn't talk about testing specific theories, but the game is always the same. In GR, you have two parameters, mass and spin. So with one mode, timescale and frequency, I extract these guys. With two modes, I test the theory. And of course, you can repeat this to your favorite theory. Just give me some theory with some extra coupling. Well, I see 2 or 3 modes, then I estimate the coupling and I test the theory. There's been a huge progress in the last decade. Actually, I have a review from 2009 or so, and I feel sorry when I look at it because there's nothing of is relevant now. It's in there. We're working in the community review. It's ongoing, should appear January or February. So I'll stop here. Thank you.
Thanks, great talk. So in addition to the quasi-neural modes, there are these, algebraically special modes that have zero real part and only imaginary part. Do they have any nice physical significance, or they're just some curious artifact of the perturbation equations?
Yeah, it's the mode with these, where the arrow is. I don't know. They are very curious. They're coming up in some things recently. It's hard to understand how they are observationally relevant. They are the 9th mode for L equals 2 and the 18th mode for L equals 3. They are so highly damped, in a tenth of a period, they're gone. But at the theory side, they pop up very often. So I don't know the answer. They're there. That's what I mean.
Thanks.
Sorry for that.
Yeah. Can you say for the nonlinear part, the nonlinear term like psi1 square, are you considering the perturbation beyond the linear perturbation theory? Is that why you have a psi1 square term?
Yeah. So the idea is to do exactly the same we did at linear order. You expand the field equations, you expand them to second order. Psi1, of course, will contain all the information of the linear guy. We know the structure for, right now, arbitrary order. So they will be sourced always by the lowest order guys.
Can I ask the field of a black hole, does it couple to the gravitational wave, and does it have any effect?
Do
Like
what?
the gravitational field from the black hole itself, does it couple to the gravitational wave created by it?
Yeah, of course.
And has a big effect on it?
I mean, this is the coupling. So if you look at the structure, at least in the context of spectroscopy, the coupling is encoded here. There are no modes once you remove the black hole. Minkowski has no modes. So the coupling between gravitational waves and spacetime is encoded in this effect.
Um, just a clarification. The study we've done assumes a Schwarzschild or a Kerr background?
Here.
Yes, in the study of the perturbations.
So
Because the decomposition in spherical harmonics, etc., makes me think that you're studying a Schwarzschild black hole.
yeah, so
So-
we know, so good, that's a very
So
good
at
question.
this point, I wonder, how do you think all this will behave in a case of a Kerr black hole? How you could use this also to extract that kind of information?
Yeah.
I wonder how the situation changes when you add spin to
Yeah.
all this
Yeah,
construction.
so my statement about knowing the structure of the ladder of fluctuations to all orders is correct for non-spinning black holes, where we know how to separate in spin 2 spherical harmonics. So this plot and the results were done for non-spinning black holes. Here, this is done for Kerr. So we know how to do second order fluctuations in Kerr. They don't separate, so the structure is not as beautiful. You need to do most of it, well, all of it numerically.
Yes.
Yes.
Ask a question, yeah. No, seriously. So I was just wondering whether about this discussion of this picking up.
Yeah. It's not me.
So about the discussion of the nonlinearities. Well, certainly there are the nonlinearities of that come from taking into account higher order in the equation you were just showing before. But I think this is a bit different from the question of the nonlinearities close to merger, where in fact you cannot maybe disentangle so well the ring down from the merger and all. So this is more maybe
I like this
these
pictorial.
nonlinearities are more the trivial nonlinearities that should be there because just you are linearizing the equation, then you go to second order, third order. Yeah, okay.
Yeah, so I like to answer that because for the past decade or so, it's very common to hear, oh, there's no nonlinearities and the waveform is so smooth because the horizon needs everything and all the nonlinear aspects of GR are filtered out by the light ring. So the first thing is they are not. They're there, you can see them. You're right concerning that then what do we mean by nonlinear, right? And certainly there's something that comes from the merger and the in-spiral. But I think for black hole spectroscopy, you could think about those contributions as initial data contributions that come from this stage, right? You're feeding, these nonlinearities are just stuff that you're feeding to the light ring, right? And then they come out after they circle the black hole a number of times. But this will tell you, this will show up in the waveform as non-constant ring down amplitudes. Those are the nonlinearities I think you referred to that are, just for me, just initial data feeding the light. They are there, yes.
Okay, maybe we can save further discussion for the break. Let's thank Vitor again.